Hey there, guys. Um, yeah, I'm out again. I wanted to make sure I was there for your lab day for tomorrow, so you got to bear with me on this video now. Wow, that's really weird imagery going on there. Camera does not look good at all. Oh well, you don't really need to see me anyway. So, capacitors. Okay, you did a little activity for me about capacitors. We're going to kind of pull in that, explain a little bit about them, try and give you a chance to wrap your head around it a little bit. I just could not do the AP Classroom video to you this time. Oh my God, this guy was so painfully boring. And that's me saying it. I know how much you've enjoyed all the other ones. This guy was special. Anyway, all right, so what is a capacitor? Okay, a capacitor is a device for storing electrical potential energy or charge, you could say. Okay, really it stores charge, and as a product of that, energy is stored. Okay, we're going to start only right now talking about parallel plate capacitors. So literally two parallel plates, and we've been talking about the field between parallel plates already, so we were heading in this direction. And from the app that you were playing with the other day, you know that we could manipulate those variables of plate area and plate separation. So obviously that's some of the big defining purpose. One of the questions I asked you is what else does it depend on? And it depends on what we put in between the plates. What we put in between the plates is generally referred to as a dielectric. I'm going to spend more time on that in the next section. But for now, it is just a material that affects the electric field in between the plates. Okay? So, to be more specific about that, when we talk about permittivity of free space, remember we've used this already. Now we might be talking about permittivity of other materials, not just free space. So you might see something called a dielectric constant in there. A dielectric constant just means that we have a constant relating to the strength of that capacitor's new medium in the middle. Okay, K for a vacuum is exactly 1. I could have gone on with zeros, okay? So when we say for a vacuum, that's why we would use epsilon naught. That implies a vacuum. Air is close enough, though, to 1 that, we're going to treat air in a vacuum pretty much like it's the same thing, even though it's not really not. We're going to see dielectric that have K values greater than 1 because it's going to increase the capacitance, the ability for it to hold charge. So now coming back to defining capacitance, we can see that capacitance then is defined by the dielectric, whatever material is in between, the area of the plates, and the separation distance between the plates. Okay? That is what defines a capacitor. Okay? Now, in terms of the units of capacitance, permittivity, we said on the previous slide, had units of Coulomb squared per Newton meter squared. Area has units of meter squared. Distance, or separation distance, has units of meters. So if I plug that all into here, I would find that my capacitance has units of Coulomb squared per Newton meter. Well, a Newton meter is a joule, and a joule is a volt is a joule per Coulomb. So we could relate it to coulombs per volt. That's a very common way. Any of these are really valid, but more common than that is that we refer to that unit as a farad. So this is a farad, this is a farad, this is a farad. Named after Michael Faraday, in case it comes up at dinner tonight. All right. We're going to be getting into circuitry a little bit more, so we're going to talk about circuit symbols. So a parallel plate capacitor is literally just symbolized by the parallel lines being connected to whatever wires. But you got to be careful because parallel lines are also used for batteries, okay? So this happens to represent a 2-cell battery. How do I know it's 2 cells? Because there's 2 sets of long and short lines, okay? You don't need to know about the cells part now. That'll come in down the line, okay? The negative end would be the shorter line. The positive end would be the bigger line. So we would say electrons are leaving here, coming into here, okay? And then when electrons start accumulating on this plate, that's going to cause a repulsive force across this dielectric, whatever it is, and cause electrons to move away from this plate back to the battery, and that would leave this plate positively charged. Okay, so that's what's represented here. You see the negative end of the battery brings in electrons onto this plate. Those electrons create an electric field, or an electric force, if you will, that's pushing electrons away from this plate, leaving this plate positively charged, and those electrons are pulled back into the battery so that the process can continue to some extent. There is a limit though, right? That's what capacitance is, the ratio of the amount of charge per volt, okay? Coulombs per volt. So the amount of charge that can be put on depends on the voltage, depends on the capacitance, okay? It doesn't go the other way though, right? Okay, so capacitance does not depend on the charge, it doesn't depend on the voltage, okay? So all that's happening here is that we're building up charge on that and maintaining an electric field in between, okay? The capacitor sets a ratio between the amount of charge and the amount of voltage. Remember when I was showing you the units back here, we said it's a coulomb per volt, okay? Well, that's charge over potential difference, okay? That's what I was going for in the little virtual lab activity when I asked you guys what the slope of the charge versus potential difference graph was. It actually was the capacitance, okay? I understand you didn't get it, just pointing that out, okay? So let me go back to that for a second and kind of make a point here, if I can. Squeeze this into the app here. Okay. So let's actually reset this for a second. So here's the app. When we turn this on, okay, we see that the negative started accumulating on. It starts making this positive, okay? If I pull out my voltmeter, you see we have 0.45 volts. As I increase the potential here, not only does the voltage go up here, but the amount of charge, because capacitance is the ratio of the charge to voltage. Now, look at this value, it's 0.3. Now I'm going to increase the voltage. Definitely more charges on here than there were before, but the capacitance didn't change. Capacitance does not depend on charge and voltage. Capacitance depends on the separation distance, the area size, and the dielectric. Now in this, we don't have an option of changing the dielectric, okay? But in theory, it's there, okay? So please keep that in mind, okay? It does not go both ways, okay? The capacitance is defined by this plate size, the distance between the plates, and the dielectric. They're going to ask so many questions in the AP about what happens to the capacitance if we increase the charge. Nothing. What happens if we increase the voltage? Nothing. The capacitor is defined by how it is made, not by what we do with it, okay? We also like to talk about electrical energy since we're storing electrical energy in a capacitor. So we had been kind of working with a basic formula to talk about the potential energy in terms of voltage or electrical potential difference in charge, but it really was an integral. And so if delta V, if I take my capacitor equation that I had given you about on the previous slide about C equals Q over delta V, that means delta V equals Q over C. And now if I plug that into my integral here, I have Q over C dQ, and when I integrate that, I would get Q squared over 2C. So potential energy could be calculated that way. But if I rewrite this equation multiple ways and substitute in, I could have gotten it as C times delta V squared over 2, or Q times V over 2. So it's not just Q times V, it is an average, really, okay, of Q times V. So that's where the half is coming into play. Okay, so the electrical potential energy depends really on the amount of charge that we can store and the potential. And the ratio between them is set by capacitance. Okay, not sure if I've made that clear, but I hope I did. Another thing we're going to talk about, and I'm going to throw a couple questions at you about this later, but we're going to cover it more when I'm back on Thursday, is this idea of energy density. Okay. Since there is a set volume between the plates of the capacitor, we often talk about electrical potential energy densities in there. So an energy density, it means an energy per unit volume. So if energy is 1/2 CV squared and V equals E times D, then, and we said that C equals epsilon naught, assuming it's the dielectric is air, C equals epsilon naught A over D, I can kind of combine those and say, all right, V squared is E times V, so that's there. And for C, I'm going to put in epsilon naught A over D and put that all together. We get something like this. So D's and A's are going to basically give me a volume, because area times distance would be volume, and the other distance cancels out with that distance. Anyway, we get this energy density here. That's what the little cursed U here is for. Really depends only on the permittivity and the electric field. But very specifically, it's really the square of the electric field. That does come up a bit. So another thing that we're going to touch on there. Okay. Again, in terms of the energy, now here they're showing it in picojoules, obviously, because we're talking about that. If I don't change the capacitance, okay, as I change the voltage, we see that the energy is decreasing because the amount of charge and the amount of voltage both are being affected, right? So as I increase the potential, we're seeing the charge increasing as well, and so as a result, the potential increases. That's something you're going to want to play with. I recommend when you're doing some of these questions today, play with this app a little bit more, because it may help you to make sense of this. Okay, and likewise, keep in mind that once I open this, obviously you found out the other day when we play with this, since the capacitor is not connected, it doesn't. It's not affected by the battery anymore, and it still stores that electrical potential. Okay, so the voltage is still 1.5 or whatever. But keep in mind now, if I start changing the capacitor around, the amount of charge on this plate and the amount of charge on this plate right now being disconnected from the circuit, there's nowhere for that charge to go. So if I start changing any of the dimensions here of this, okay, you'll see that I'm changing the capacitance, I'm changing the stored energy, but I'm not changing the charge. Look at those pluses and minuses on that thing. Let me take off the electric field. You'll see the pluses and minuses are not changing, but I can change the energy, and I'm changing the voltage just by changing the capacitor. Okay? Since the charge can't change, it has nowhere to go. When I change the capacitance, I'd have to change the voltage. I'd have to change the energy of the system. All right, so I hope this helps a little bit get you going on it. I have a little packet of questions. Please turn it in before you go, whatever you get done. And yes, it should be easy enough for you guys to crank out together. All right? Let me know if you have questions. Talk to you soon. Bye.